Hello everyone, and thanks for having me to give this presentation. I'm Marina, a PhD student at Niels Bohr Institute. Today I'm going to talk about a fairy tale story. This is partially based on work that I already did with collaborators Simone Albanese and Gregorio Carullo, but you will also see some recent work in progress, very exciting results. So what are we focusing on? We're focusing on binary black holes mergers. So usually we know that we can divide such systems into three different stages. We have initially an inspiral in which we have the two objects orbiting around each other. The orbit is losing energy and angular momentum since it's emitting gravitational waves, and so it's shrinking up until at some point the two objects form a common horizon. There is a merger, but as you can see here, this object is quite deformed, and it takes some time to relax towards a final equilibrium configuration. And in doing so, it emits a radiation that is well approximated by the exponentially damped vibrational modes of the black hole. And for this reason, we call this part the ring down. Now, what we're going to discuss today is the late time part of the signal. So basically, what is left after the main body of radiation has decayed. And for this reason, we call this part the tail. So I'm gonna first start with a brief introduction about what was known in the literature, and mainly we're gonna discuss about tails in a perturbative setting, so considering first order perturbations on a Schwarzschild background, driven by just initial data. Then we're going to discuss phenomenology of tails and an analytical model to describe tails in the case in which we still have perturbations on a Schwarzschild background, but this time this problem is driven by the presence of a source that is infalling in a black hole. So we're going to discuss tails in extreme mass ratio mergers. Now we're going to use the understanding coming from this problem, this limit, to understand how we can extract tails in fully nonlinear numerical relativity, so in waveforms of binary black hole mergers of equal mass ratio. So let me stress why this is why I think this is a very important matter. So first of all, tails are a foundational problem in general relativity. So we have a lot of possible tail signals. For instance, a lot of new tail signals were predicted in the context of the classical soft graviton theorems. You can find here a nice recent review that came out this summer by Shoge-sen. And this found that some of these tails actually violate the peeling properties of the spacetime towards non-infinity. And it was actually found later by Gashik and Kerenberg that this can also imply a modification in the late-time signal following black hole perturbation. So in general, I think that tails are very interesting because they can allow us to probe the asymptotic structure of the spacetime. But other than this foundational problem, we also have astrophysical implication of tails. So as I'm going to show you in a moment, the post-merger tails are highly enhanced with the eccentricity of the progenitors binary. So first of all, this makes tails potentially observable, but then we know that there are also plenty of possible channels for highly eccentric mergers. And actually, there is also evidence that recently the LBK collaboration already detected a very eccentric merger following a dynamical capture. But then if we can observe tails in such settings, that could help us give constraint on the parameter of the eccentric spiral. And this is very important astrophysical information relevant for studies on binary formation or population. So let's start with the review, let's say, of what was known in the literature. And I'm going to keep it quite short, but I think it's important to understand the problem. So we're considering linear perturbation on a Schwarzschild background. So these are described by the Regge-Wheeler-Therilli equation without a source because we are considering just an initial data-driven problem. And so we give initial condition at a certain initial time. Then, given this problem, the general solution is a convolution of a source built from the initial data that you can see here, and then a propagator. Now, we are focusing on the late-time signal, so we would like to isolate the, let's say, propagator that describe tails. This was done by Price and Lever in the literature. And how we do it, how we isolate this propagator. So first of all, we go in the complex frequency domain. And then the green function, by definition, is a solution of this impulsive problem. And then to isolate the tail component, we use this intuition that tails are originated by the backscattering of small frequency signals with the long-range structure of the potential. So you can see here a very schematic representation of this potential in the Regge-Wheeler-Zerilli equation. And the main point is that you can see that it falls off a large R in a kind of a slow way. It's not compact. It has actually a polynomial tail in R. And what happens is that very low frequency signals can interact at the large distances with this slow fall off of the potential and are backscattered, so generating tails. So starting from this intuition, to be able to isolate the part of the propagator to describe tails, we need to expand in large distances and, of course, small frequencies, because those are the ones that can probe large distances. So by expanding the Regge-Wheeler-Zerilli equation in large R, we can obtain a column-like wave equation. And we solve this equation in small omega, small frequency. And then, of course, we need to compute an anti-transform to go back to time domain. Now, the interesting thing is that you see that there is this complex logarithm that implies that there is a branch cut in the complex plane. So when we do this interval, we're actually doing the interval along this complex contour that you see here. Now, these 2/4 of circumference don't give any contribution because we're pushing omega to very large values. And you can see that only the branch cut, so this 2 part of the contour, gives contribution. And this again confirms also our initial assumption that we are focusing only on part of a signal that is at very small frequencies. So once one solves this integral, and then we convolute this Green function with the initial data source, it is possible to obtain a prediction for the late time signal for tails at non-infinity. And it was found in the literature by Price and Lever that this signal follows an inverse power law decay, in which the amplitude that you see here is actually a constant and only depends on the initial condition. This is denoted as Price law in the literature, since, again, it was found initially by Price. Now, the point is that it was not really thought that this signal would be something interesting, let's say, because in the literature in the past that you can find, this signal was always thought to be suppressed, so too small to have really, no one really looked into what is information content carried by tails, so what we can learn from tails. Now, this picture changed last summer because there was an interesting paper by Simone Albanese and collaborators that came out. And what they did is to compute numerical perturbative waveforms, again considering perturbations, linear perturbations on Schwarzschild background, but driven by a source, a test particle, that is infalling in the central Schwarzschild black hole, following generic trajectories. So they analyzed both a quasi-circular case that you can see here in blue, and then increasing the eccentricity up to very eccentric mergers in red. And you can see here the results for the 2-to multiple of the strain versus the time from the light ring crossing up to late times. So, of course, initially there is a part dominated by quasi-normal modes that we can see because it has quite a sharp decay, because quasi-normal modes, as we know, are exponentially damped. But after a while, there is a slower decay that kicks in. And this is the tail-dominated part of the strain. Now, what is interesting is that you can see that the amplitude of the tail is enhanced by several orders of magnitude with the eccentricity of the progenitors binary. So for instance, here there is an enhancement of 10 to the 4 going from a quasi-circular to a very eccentric configuration. Now, this was an interesting phenomenology, and it wasn't really looked much farther into. So the first thing that I did with my collaborator was to ask ourselves, does something similar holds even for comparable masses mergers? So this led us to analyze the waveforms of the RAT catalog. This is a public catalog that has fully nonlinear waveforms, also for eccentric mergers. And you can see here some of the most eccentric configurations that they have. And the demonstration in this case is 1, and we were able, with some Bayesian inference techniques, to actually show that there is a post-merger tail And it follows a similar enhancement as to what was found in the test particle case. However, we were still unsure about some points of this analysis, and the main, let's say, weakness of this analysis was that this signal is not properly extrapolated at non-infinity, and I'm going to show you later that this is actually a key feature. And then you can see that in a comparable masses case, there seemed to be a much larger enhancement than what was found in the test particle limit. Now, the main problem is that we didn't really understand why this enhancement was happening, what even was this late time signal, let's say, if it was described by Price law or not. So what we decided to do was to go back to perturbation theory and try to understand tails in a dynamical background. So we have of the test particle that is driving the perturbations, and then ask ourselves if tail can really be still explained by Price law, or if we need to go beyond this and build a model that is a bit more complicated. And this is exactly what we did and what we're going to discuss now. So we consider a test particle infalling in a Schwarzschild black hole using perturbation theory. And the signal is always computed at null infinity. And this is important because we can approximate that our detectors are at future infinity, null infinity, but also because Price law changes, let's say, its decaying behavior when observed as square plus as compared with finite distances. And at finite distances is also suppressed. So we're always going to focus at the future null infinity. Now, we perform some perturbative numerical evolutions to start with, and by solving the Regge-Wheeler-Terilli equation, but this time with null initial conditions, because we want the perturbation to just be driven by this source that you see here. This source is localized at the particle trajectory, and so in order to solve for this signal, for this system, we also solve the Hamiltonian equation of motion for the trajectory. Now, we introduced in this equation of motion some radiation reaction effective forces. So these basically are enclosing all of the information on the fluxes of energy and angular momentum at infinity and are computed analytically. And this is a very important point because this allows us to evolve generic orbits up to mergers. So we do not have to consider only geodesic plunges, but we can, for instance, consider also dynamical captures. So a case in which initially the test particle and the black hole are unbounded, then after some time, due to, again, radiation reaction, the system becomes bounded, forms an incredibly eccentric binary, and then eventually to merge. Now, another key point of this analysis is that we used a code that is the RWZ hyperboloidal code that has an hyperboloidal layer that is attached to the computational domain inside which the trajectory is evolved. And in this hyperboloidal layer, their star coordinate is compactified. So this means that we can have null infinity at a finite distance, and so we can include it in the computational domain. So we do not have to come up with difficult methods to extrapolate the signal at null infinity. We can directly compute the radiative signal at null infinity. Now, other than having some numerical evolutions, we also wanted to build a model that was able to describe the late-time tails. So to build a model, we take again our problem. And since we are imposing null initial condition, the most generic solution for the field observed at square plus is a convolution of the source with this propagator. Since we are focusing on the late time part of the signal, we choose as a propagator, Price law propagator. And considering that the source is can be written in this way, so it's localized at the particle trajectory, then we can come up with an integral model to describe the late time signal that you can see here. Now, there are two things that we need to notice, let's say, at this point. First thing, this is an integral model. So it is telling us that what we see at late times, at late retarded times tau, is actually an integral over the whole past history of the system. So it makes manifest the fact that tails are memory effect, even though it's more correct to say that they are an hereditary effect, because it is telling us that the post-merger tails are actually inherited by the inspiral. And in order to understand this point, we can use this schematic representation. We have here, this is the trajectory that the test particle follows while it's infalling in a black hole. And then at each point of this trajectory, the test particle will emit gravitational waves. Now, part of these gravitational waves, and are the dashed lines here, directly travels, is the direct signal, and travels on a light cone towards non-infinity. But then there is another part of the signal. It is the one that has a small frequency that can interact with the long-range curvature of the space-time, so with the tail of the potential describing the background, and it is backscattered. And so let's say that it takes more time to reach non-infinity. So it is effectively traveling with all of the velocities inside the light cone. And so this is why, even at very late times, after the merger has occurred, we can still see some information that was emitted during the inspiral. Now, other than this point, I think that there is another important observation to make, and is that in general, this is not inverse power law behavior. There is an inverse power law, but it's convoluted in a complicated manner with the source. So we can expect a phenomenology that is a bit more complex than just price law. But however, in order to validate this model, we need to test it against numerical evolution. And this is what we did. So the thick lines are the perturbative numerical evolutions obtained with the code that I described before. And the dot dash lines are the prediction of our analytical model. You can see here the results for different eccentricities, so going from a quasi-circular up towards very high eccentric cases. And so what we can see is that for intermediate to very high eccentricities, our model is able to, let's say, predict properly the tail signal from the moment it starts to dominate over the quasi-normal modes up to late times. It seems to fail, let's say, for small and eccentricities and the quasi-circular case. It's only able to, let's say, predict the general orders of magnitude of the tail. And this has two possible explanations, this mismatch. So the first thing is that for a quasi-circular case, the tail starts dominating when the signal is very low. So there is numerical noise that can impact, let's say, the numerical evolutions. But then if you remember, we derived the model using a price law propagator. Price law propagator is computed under the assumption that we are at large distances from a black hole. Now, if we have an eccentric orbit, this is true for a large part of the whole inspiral, right? Because the test particle spends a lot of time away from the black hole, even for times close to the merger. But this assumption starts to fail if we consider a quasi-circular inspiral, because in this case, for times close to merger, the test particle spends a lot of time actually close to the black hole. So let's say that the generic assumption that we made at the beginning to derive the model is failing. And so this is a possible explanation for this mismatch. But however, now we're going to focus on intermediate to high eccentricities. And we can define the tail exponent to, let's say, study more properly the late time behavior of these tails. Now, from, let's say, initial data-driven perturbation theory, we expect a tail exponent that is converging in a monotonic way towards -4 in this case, because we are considering the 2-to multiple of the strain. Now, the interesting thing to notice here is that even on a very large time scale, this tail exponent does not seem actually to converge towards -4, but not only this, the behavior is actually non-monotonic and it exhibits this sort of oscillations. And so it has, let's say, a more rich phenomenology than what is just expected by initial data-driven perturbation theory. So let's stop for a moment, let's take a breath. We have found an integral model that is able to describe tails in extreme mass ratio mergers, and the mix manifests the fact that tails are an hereditary effect that brings information about the whole history of the system at very late times. And we have observed an interesting phenomenology. In particular, we noticed two things. First of all, in general, the tail exponent is non-monotonic and it relaxes in a very difficult, let's say, complicated manner and on large time scales towards something that seems to be converging towards price law. And then we have noticed that the tail amplitude is highly enhanced by the eccentricity, as it was actually already known. But so, since we have a model to describe tails, we can use this model to understand this phenomenology. And we're going to start with the first one. So what we are going to do is to consider an observer that is at very late times. So after a common horizon has formed, or in this case, after the particle has plunged in the black hole. And then what we do is that we take our model and we perform an expansion in this limit. And this is what we obtain. So our model predicts now that the very late time signal is a superposition of power laws. The slowest decaying term is price law. So this means that at asymptotically late times, we know that we will always recover price law. But then there are faster decaying corrections that are faster decaying power laws. And each one of those power laws has an excitation coefficient that depends both on the amount of history that we are considering, but also on the specific orbit that we are taking in consideration that is enclosed into this function of the source of the trajectory. So the point now is to understand what is the relevance of these faster decaying terms, because if they're highly suppressed, if they're not really excited, then these probably don't really matters, but they can also give rise, let's say, to a long-lived transient if they're very excited during the spiral. In order to do this, what we did was to take this model as superposition of power laws and test it against the perturbative numerical evolution. And now the line in gray that you see here in these two plots are the result of the numerical evolution for a dynamical capture. So a configuration in which initially the test particle and the black hole are unbounded, then at some point the system becomes bounded and ends in an extremely eccentric merger. And then we compare this numerical result with analytical prediction for a different number of power laws. N equal to 0 means that we're only considering the slowest decaying term, so we're only considering price. And then we can add other corrections, let's say, by using this, computing the excitation coefficient of each term. Now, what we find is that in order to be able to reproduce, let's say, the numerical waveforms from the moment in which the tail starts to dominate the quasi-normal mode, so from this time, really a large number of power laws need to be taken into account. And that indeed, at very late times, we can recover the case of n equal to 0, so just price law. But as you can see here, this is an incredibly long time scale. This is a selected simulation that was really long-lived, and it's only after 10 to the 5 m after the Leitner crossing that we can actually recover price law. So this means that all of these faster decaying terms give rise to a long-lived transient that is really everything we care about from an observational point of view. And not only this, another interesting feature is that in general, the source is something that is oscillating, it's not strictly positive. So also the excitation coefficient of each of these power laws doesn't have to be positive, strictly positive. So different power laws can interfere with each other. And this can explain why there are these oscillating kind of behaviors in the late time signal, why this is not a monotonic relaxation, because this is due to the fact that there are different power law terms that are interfering destructively with each other. So using our model, we were able to find that the tail is actually in a dynamical setting, is not an inverse power law decay, but is a superposition of a lot of power laws. And only at asymptotically late times, we recover price law. Now we're going to focus on the tail enhancement with the eccentricity. So the key point is that we have seen that tails are an hereditary effect. So they depend over the whole, let's say, inspiral. If we want to understand why tails are so enhanced with eccentricity, we need to isolate exactly which part of the trajectory of the spiral really determines the amplitude of the tail. And we're going to focus only on the amplitude of the tail by the stars this signal becomes actually visible, so starts dominating over the quasi-normal mode. And to isolate this part of the trajectory, we performed a series of, let's say, numerical experiments. So we take our integral model and we change this the time at which we start integrating. So what are we doing? At an operational level, we can take a full trajectory that you can see in this schematic representation as the gray line. And then we start cutting it. So we start integrating always later and later and later. So for instance, here on the left, we start integrating from the second apastron before merger. Here in the center, we are starting to integrate from the last periastron before the merger, or we can also start integrating directly from the last apastron. The key point is that we expect that the more history we include, so as we go towards the left here, at some point we will need to obtain like some convergence. So because we know that our model is able to correctly reproduce, let's say, the amplitude of the tail for very eccentric settings. So you can see the results of these experiments here. This is the amplitude of the tail by the start dominating over the quasi-normal modes versus this initial time, T-in, of integration for different eccentricities. And as I was saying before, as we go towards the left, we are including more and more history. And so we expect to converge towards the numerical results that are the thick opaque lines that you can see here. Crosses means that we are starting to our integration of our model at an apastron, dots that we are starting the integration at the periastron. Now this, let's say, experiment seemed to show that the tail amplitude is determined mainly by the motion that is happening near the last apastron. In particular, if we consider an extremely eccentric merger, then only the motion from the last apastron is enough to be able to recover, let's say correctly, the tail in the post-ringdown phase. If we consider intermediate eccentricities, there is this sort of bumps that appears that seems to imply around the last apastron, that seems to imply that there is some cancellation going on between the in and outgoing motion near the last apastron. But let's say that this experiment only gives us a general intuition, but it's an important intuition because then we know that if we want to extract something more concrete from our model, we can in general perform an expansion in large distances and small angular velocity. That are the conditions that are satisfied by the motion at an apastron. So performing an expansion in these limits, this is what we obtain for our from our model. And you can see that the integral is indeed enhanced by a motion that is happening at large distances. But more importantly, there is this phase factor over here. So this phase factor, if the angular motion is very fast, it will oscillate a lot. So this means that once we compute the integral, this quantity will be highly suppressed. And so it's really what is controlling the fact that the more radial a motion is, the more enhanced the tail will be. Because otherwise we can interpret it as saying that tail signals that are generated by closely to each other just continuously destructively interfere with each other. But so in the case in which we have a radial infall, then this quantity is just one, and then it's constant, it's not oscillating anymore, and so we have a maximized tail emission. And indeed, this is what we found, is that tail emission, radial inflows from large distances always maximize the most the late time tail. But not only this, and this is another, I think, very interesting point, is that this piece, let's say, is equal to 1 also if we just analyze the 2-0 mode, for instance, so every mode with m equal to 0. And actually we saw in from numerical evolutions that even if you consider just a quasi-circular spiral, so in a case in which in the 2-2 mode the tail is suppressed, the tail of the 2-0 mode is actually very enhanced because this phase factor is just a constant, disappears, let's say. And so this is very important for future observability, let's say, studies of tails. So what happens when we have instead a very eccentric merger? So the main point is that if we have a very eccentric last orbit, the larger is the eccentricity, the further is the position of the last apastron. And not only this, but due to Kepler's second law, we also know that the test particle will spend more time near the last apastron because its angular velocity will be smaller. And so this means that the larger is the eccentricity, the more time the test particle will spend in a location in which it's emitting a very enhanced tail. And this is a very interesting point for me because So when we talk about all of the signal that is in the post-merger phase, we have this intuition that is generated very close to the black hole, right? So either at the merger or just at the light ring crossing, because this is where the quasi-normal modes are generated. But this is actually telling us then for what concern tails, this picture changes. And the tail that we see in the post-merger is actually emitted at the last apastron, so very far away from the black hole and much before the merger has occurred. Now, if we consider instead more, let's say, less eccentric case, then we will have to take into account other terms in our expansion in the angular velocity. And then there is this term that appears, and this term directly depends on R dot. And so this is actually explaining why there are these bumps, because R dot changes sign, and it can induce like cancellation between tail signals that are emitted in the in and outgoing motion just near the last apastron. So let's say that we are able now to understand this phenomenology and the tail enhancement with the eccentricity, because we have seen, thanks to the model, that the tail emission is enhanced for motions that are happening at large distances with small angular velocity. And more importantly, that the tail emission is maximized at an apastron. So for eccentric configurations, the tail that we see in the post-ringdown phase was actually emitted at the last apastron before the merger. Now, we can use all of this information that we gather from this, let's say, perturbative case in a dynamical scenario to go back to the comparable masses case. So to dig out... Yes.
I want to ask a question. It's so if I understand this, so did you have a look at the finite distances? I'm almost thinking that at finite distance you wouldn't see this kind of behavior if you're not too far away from the black hole.
You mean the enhancement with eccentricity?
The dynamics. I mean, I'm not sure. I'm just conjecturing here randomly, but it seems to me that this is specifically a memory thing of what the particle has been doing in different parts of the potential, and so this accumulates in some sense through backscattering off of curvature at null infinity. But if you were at like finite distance, I'm assuming it wouldn't be as visible. I was wondering if you did the analysis, because the tail back in the day, everybody was looking at the tail behavior at finite distances. Null infinity wasn't. Of course, Price did both of them, but many numerical simulations were at finite distance. I'm wondering if you tried that.
Yes, this is an excellent question, actually. And so we analyzed, we look at finite distances, and indeed, the tail is highly suppressed. You can still see scaling, let's say, with the eccentricity that is the same type of scaling, but the results will be highly suppressed. But this is actually a very good point for what I'm about to explain for extracting tails in fully nonlinear mergers. So I think that I'm gonna answer better to this question in a few slides, if you can wait.
Sure, thank you.
Yes, but this is actually a very good point indeed. Because again, now we want to go and extract tails in fully nonlinear simulations, and so let's start with a generic. But I promise I'm gonna answer to this question. Just give me I think 5 slides, and then we're gonna go back to it. So so let's go back to the fully nonlinear case of equal masses mergers. And let's go back to our initial analysis, understand what was wrong with the previous analysis and how we can improve it to extract tails in this case. So the first thing is that we were looking at waveforms of the arity catalog that solves for psi4. It's connected to the strain by a double derivative. And so this means that we will have a suppressed tail. And of course, if we are looking at tails in fully nonlinear numerical evolutions, we have a considerable, actually, noise floor, let's say, of numerical error. And so we want the tail to be as enhanced as possible, not suppressed, because we also would like to follow the evolution long enough to be sure that we are actually extracting a tail signal and not some other kind of numerical artifact. So what we could do is to perform a double integration in time domain, but this is bad because it will just enhance the noise because it just accumulates when integrating. We could also do what is standard procedure, at least for the RT catalog, and is to perform a double integration in the frequency domain by using this relation that tells us that the integral in time of a certain function is equal to the inverse Fourier transform of this quantity, where h tilde is the Fourier transform of h. Now, there is, however, a subtlety, and it's that all of our signals are finite in time. And if a signal is finite in time, it doesn't last forever, let's say, as basically all of our physical signals are finite in time, then once we go and do the Fourier transform, there will be a spread in the frequencies. And so since there is this omega at the denominator, this can mean, this procedure to do this integration, that we are enhancing physical features at low frequencies. So what is usually done to perform this integration scheme is to introduce a cutoff frequency at very low frequencies, such that the quasi-normal mode part of the strain is not affected. But however, the signal is a small frequency, the tail is a small frequency part of the signal. So we were actually able to see after further analysis that this cutoff can induce spurious effect in tails. So this is not actually a framework that we can have. We need to obtain something that directly solves for H. Then another thing, and this is again to your previous question, Anil, is that DRT solves for signal at finite distances, and then it extrapolates to square plus. And now, if this extrapolation procedure is not under control, then it will induce systematics in the tail extraction. So first of all, I want to just review a bit how we do these extrapolation techniques for people that are not familiar with it. So the waveform is computed at extraction radii, certain extraction radii. Then we build a coordinate that in the limit of r going to infinity acts as a null coordinate, and we compute the strain at each time step along this extraction radii. And then for each time step, we fit the waveform along this extraction radii with this polynomial expression that actually follows from Peeling theorem. And n here is the order of the extrapolation. And the only thing that we require is actually that this procedure need to be converging in n. So of course, if we consider higher or just a lower extrapolation order by a factor of 1, we need to obtain something that is more or less converging. And then the signal at null infinity is extracted using this relation that, again, this follows from what is expected for asymptotically flat spacetime following Peeling theorem. But where is the subtlety in this? Is that if the extraction radii are too close to the black hole, we are effectively cutting a tail contribution. Because again, as we discussed before, the tail is generated by the backscattering from the long-range curvature of the space-time. So it needs, let's say, enough space to literally evolve. So if we take these extraction radii that are just too close to the black hole, we are cutting a part of the space-time that is generating the tail signal. And so we are effectively quenching the tail evolution. And so this is indeed why we could obtain a suppressed, let's say, signal when we extract tails too close to the black hole. And so this is something that of course, we need to take care of, and to understand how to, let's say, make this procedure converge, what we did is to perform some, let's say, numerical experiment. We took our perturbative waveforms, computed with the same code that for all of the results that I showed you before. And as I told you, this code allows to obtain the signal directly at square plus, but it also allows to extract signals at finite radii. So for instance, you can see here the strain computed from the peak up to late times for a radial infall. And the line in black is the signal computed by the code at null infinity. Then in the color here, you can see the signal that is computed by the code at finite distances. And we push the finite distances large enough so that this suppression is not too large. And somehow the tail had, let's say, enough space to evolve and it's not quenched. And then we perform the extrapolation technique that I discussed in previous slides. For extraction radii inside in this interval that you can see here. So from this minimum value towards this maximum value of the observer location. And you can see the result for the extrapolation in the dot dash line in purple. So what you can see is that this procedure, if we push the extraction radii large enough, this procedure seems to be able to reproduce, let's say, the waveform that is supposedly seen at square plus. Of course, this only will hold for a limited amount of time before these two behaviors starts diverging. And so let's say that the key point here is that the farther you go in this, the farther you push this position of the observers, then you obtain something that is converging for more time towards the signal at square plus. So your extrapolation technique will be more robust, let's say. But of course, if we also saw that indeed, like the opposite applies. So if you choose observer positions that are just too close to the black hole, this procedure does not even converge in the extrapolation order, because what happens is that you're really just cutting out all of the region of the spacetime that is allowing the tail to evolve and to be emitted. So you're just quenching this effect. So this is actually a key point that we need to tackle when we're looking at tails in fully nonlinear mergers, because at the moment we do not really have codes, at least the measure codes only solve for results at finite distances. And so we really need, let's say, a clever framework to extrapolate this signal at square plus. So we are taking all of these subtleties into consideration and redoing an analysis that is a more robust analysis, and I'm going to show you now some exciting results. First of all, we are using waveforms of the SXS collaboration that solves for the strain, doesn't solve for psi4. So this means that no integration is needed, and we have removed, let's say, the first weak point of our previous analysis. However, there is a downside, unfortunately, and is that all of these waveforms of the SXS collaboration are characterized by a late times constant that we're not actually quite sure if it is memory or gauge effects. I think it's the latter. But anyway, it just spoils the tail extraction. So we are analyzing actually H dot to remove this constant term. So then we need to choose what is the best configuration to obtain a robust extraction of tails. And we have two requirements at the moment. The first of all, we want a signal that is as enhanced as possible, because we need to be able to follow its evolution for a lot of time in order to really be sure, let's say, that we are seeing late time tails, so a physical effect, let's say. And then we would also like to compare the prediction from, let's say, the fully nonlinear numerical waveforms with predictions from perturbative, from perturbation theory. So to, let's say, satisfy these two requirements, we can choose radial infalls, so, or full head-on collisions, let's say, because as I explained to you before, the maximum enhancement that we can have for the tail is for a motion that is radial from large distances, so purely radial. And you can see here on the right, we have perturbative waveforms obtained from different initial separations. And you can see that indeed these are much more enhanced with respect to the eccentric configurations that we discussed before. So studying radial infalls from 100 or 200 M is actually a very good starting point to obtain an enhanced tail. But then there is another requirement that we discussed before, and it's we want something that can be compared with the perturbative results. But well, the main problem is that when you have fully nonlinear mergers, even if initially the black holes don't have spin, then due to conservation of angular momentum, the final black hole will have spin. And of course, in the perturbative results, we are in the opposite case. So we are always considering Schwarzschild background. But if we consider head-on collisions, if initially the black holes don't have spin, even the product black hole will not have spin. So we will able to make, let's say, a more fair comparison between fully nonlinear and perturbative results. So we are analyzing head-on collisions with different initial separations, starting from R0 equal 100 m, with the waveforms of the SXS collaboration. And the last, using again large extraction radii for the extrapolation. And the last subtlety that we need to take into account is the boundary of integration very far away. Because when the signal reaches the boundary, part of the signal can be reflected, and then it can, let's say, contaminate the waveform extracted at the extraction radii. So we are pushing the boundary at very large distances, such that is never in causal contact with the waveform along the whole evolution of the signal. So I'm going to present you now some exciting results. These are this is a comparison of perturbative waveform, that is the dashed dot line, with the fully nonlinear waveform, that is the black line that you see here. For the black line is obtained for head-on collision from 100 m of initial separation, equal masses, so mass ratio equal to 1. And again, I'm showing you the amplitude of h dot, because otherwise we would have a constant at late times contaminating the signal. And the perturbative results are obtained for a test particle that is initialized from the same distance and with the same, is such that this perturbative system has the same initial ADM energy of the equal masses system. And then, of course, the perturbative waveform has to be rescaled by this factor, where mu is the mass of the test particle, but in the limit of test particle mass that is very small, then this is just the reduced mass of the system. So we're basically rescaling the waveform such that it has the correct, let's say, reduced mass. That is 1/4 for a mass ratio equal to 1. Now, interestingly, and very unexpectedly, at least for me, the match is incredibly good, actually, from the peak of the strain up to very late times. And but we're now focusing on the tail part of the signal, so this late time part. You can see here on the right also the tail exponent. And so the time at which the tail starts dominating is well, more or less the same as what was predicted by perturbation theory. However, it seems that the equal masses waveform has a slower decay than respect to the perturbative waveform. And this could, again, probably also be due to some other numerical subtleties that we're going to discuss in a moment. But I want to stress that this is probably, actually, I think it is, due to nonlinear effects. And this is very exciting because usually we think about nonlinearities as if they are mainly dominating the initial part of the merger, right? We have a nonlinear initial transient, and then we have something that is well approximated by linear perturbation theory. But the nice feature about tails is they are an hereditary effect. So they accumulate everything. So accumulating nonlinearities means that in the end, they will be able to amplify nonlinear effects. And in particular, there are 3 directions that we will in the future explore to understand better the nonlinear content of the late time tails. And first of all, it's we are considering in the perturbative results a source that is linear in the symmetric mass ratio. But we will have probably to take into account more, let's say, higher order corrections in order to have a trajectory that is more, let's say, faithful. There could also be that there are some second order tails. And these are, for instance, there is a beautiful result by Okuzumi and collaborators in which they were able to find that a a 1 over tau tail, so a slower decay than what is usually priced, as a second order effect that actually doesn't depend on the branch cut at all. It's just, let's say, a convolution of the prompt response propagator with linear order quasi-normal modes, and is a result that we reinvestigated also further recently. So it could be, again, the presence of second order, more complicated tails, but it could also be that the background is actually evolving. So if we have a test particle that is infalling in a black hole, and the test particle has a mass that is very small, it will emit gravitational waves, of course, and the black hole will absorb part of these gravitational waves. But since the amplitude of this train is very small, then can totally neglect the horizon absorption effects. But as we increase progressively the mass of this test particle, then at some point we need to take into account the fact that the background is not static, but is actually evolving, because the black hole is, let's say, accreting gravitons. And now this is very important for tails, because tails are generated by basically the interaction of low frequency signals with the mass monopole of the background. So if the mass monopole is changing, as in the case of a dynamical background, then we will have a change, of course, in the tail effect. And this would particularly be interesting, I think, because it would be, let's say, a third order perturbation theory effect, maybe also in the late time signal. But however, there are a lot of directions that we need to explore, let's say. First of all, we need to, what we are doing actually is to repeat this let's say, analysis of tails in fully nonlinear waveforms for different R-naughts, and then see if we obtain a scaling that is similar to what is predicted from perturbation theory. We're trying to test the phenomenology for different mass ratio to better understand if this slower decay is actually due to nonlinearities, and if so, what is exactly the phenomenology going on there. We're studying higher multiples, but more importantly, we're trying to implement a Cauchy characteristic extraction scheme. So this will be able, because yes, so the extrapolation that we are now using is something that is more robust than what we used before. And since we are, again, just studying tails for a limited portion of time after the merger, we believe that it is actually robust and it's converging. But however, this would be probably one of the best way to, this is the best way to evolve the signal at non-infinity, because it would allow us to really evolve the signal and not just extrapolate it. So I'm going to conclude with some, we have seen in this talk that we have derived an integral model for tails in extreme mass ratio that makes manifest the fact that tails are an hereditary effect. So the post-merger, post-ringdown tails are inherited from the inspiral and carry at very late times information over the whole past history of the system. We have seen that the presence of the source makes the tail be a superposition of inverse power laws. So in a dynamical setting, we do not have just an inverse power law decay that is priced, but we have faster decaying terms that dominates a long-lived transient and are relevant for observations. And we have seen that the tail emission is enhanced for a motion that is happening at large distances from the black hole with small angular velocities. So this means that the tail emission in an eccentric merger is maximized at the apastron. And so the tail that we actually observe in the post-ringdown was actually emitted at the apastron, so very far away from the black hole and much before the merger. And then we have robust hints of the presence of tails in equal masses mergers from fully nonlinear numerical relativity waveforms. But this is only 50% full, because I think we still have some work to do to finish this work. And I'm going to conclude also, because I'm short of time, with some general future directions, and is of course to try to extend the model to care, so understand tails in a dynamical setting, but in which the background is now a Kerr black hole. Study tails in dynamical spacetimes to understand if indeed we can have the presence of, let's say, third order nonlinearities in the late-time signal after binary black hole coalescence, and then study what happens to tails in environments. Because if we have an environment that has low density and is very extended, then it's also complicated to be able to probe this environment with ring-down observation. But the tail depends on the large-scale structure. So probably the tail signal will be more affected, and I think it's an exciting prospect to gauge exactly what are the effects of an environment of tails. And of course, this all goes in the direction to study all of the complexities of a realistic merger, because the final goal is to estimate the observability of tails with LISA and to understand all of the possible physics that we will be able to learn in the future, hopefully, with tails observations. And just as a final remark, I think that tails are incredibly interesting because we have black hole spectroscopy that allow us to make probes of the small scale of gravity, let's say. But just right after the ring down, we have a whole new part of the signal that is not only tails, also memories, that is contains complementary information, because it's information on the large scale structure that is equally interesting, I think, and so it makes really an exciting prospect for the future to start focusing the attention also on the late time part of the signal. And with this, I conclude. Thanks a lot.